Did you know that Netflix generates over 500 terabytes of data times everyday times? 90% of that data is unstructured or semi-structured, making it difficult to analyze with traditional databases. Here's what most engineers get wrong. A data lake isn't just a storage dump. By the end of this video, you'll know exactly how to design a data lake that unlocks insights from raw data. Remember this Netflix scale number. We'll see why it matters when we discuss scaling. Now that we've established the scale, let's define the problem. A data lake is a centralized repository that allows you to store all your structured, semi-structured, and unstructured data at any scale. Functional requirements include ingesting diverse data types, storing raw data in its native format, and providing access to various data processing frameworks. Non-functional requirements are scalability, security, and data governance. Clarifying questions. What data sources will be ingested? What are the data retention policies? What are the data access control requirements? We need to support data variety, including logs, click streams, sensor data, and social media feeds. It's critical to store raw data for future analysis and compliance. This is where the concept of Schema-on-Read comes in, which we'll cover in detail later. This sets us up for the deep dive into estimation. Let's assume we ingest 1 TB of raw data per day. Over 1 year, that's 365 TB. With a 3x replication factor for durability, we need approximately 1.1 petabytes of storage. For bandwidth, if we ingest data at a constant rate over 24 hours, that's TB, 86,400 seconds, equals roughly 12 megabytes per second. However, we need to account for peak ingestion rates, so let's provision for 10x that, or 120 megabytes per second. Stop. Think about this. These are sustained rates, not burst rates. Remember these numbers as they'll inform our architecture choices. With the foundation in place, let's tackle the high-level design. We'll use a distributed object storage system like AWS S3 or Azure Blob Storage as the foundation for our data lake. Data ingestion methods include batch processing using tools like Apache Spark or streaming ingestion using Apache Kafka. Data processing frameworks include Spark, Hadoop, and Presto. To access the data, we'll define a REST API, get.api v1.data.file path. This API returns the raw data. Here's where most engineers make a critical mistake. They treat the data lake as just a storage bucket. The key is to design for efficient data discovery and governance. We use object storage because it offers scalability, durability, and cost effectiveness. HDFS was considered, but object storage offers better integration with cloud services. This brings us to a crucial challenge: understanding Schema-on-Read. Unlike a data warehouse, a data lake uses Schema-on-Read, meaning the data schema is not defined until the data is queried. This allows for greater flexibility in ingesting diverse data types. The core service logic involves defining data processing pipelines that extract, transform, and load data into a usable format. A common candidate mistake is failing to differentiate between a data lake and a data warehouse. A data warehouse uses Schema-on-Write, meaning the data schema is defined before the data is ingested. This is suitable for structured data and predefined analytical queries. Now, at this point, your interviewer will push back, why not just use a data warehouse instead? Here's how you defend this. A data lake is ideal for exploratory data analysis and machine learning, where the data schema is not known in advance. A data warehouse is better suited for structured reporting and business intelligence. We use Schema-on-Read because it allows us to ingest data without knowing the schema up front. The trade-off is that query performance can be slower. Building on that architecture, the next bottleneck is metadata management. Metadata is data about data, providing information about the data's origin, format, and quality. We need to store technical metadata, schema, data types, business metadata, data owners, descriptions, and operational metadata, data lineage, audit logs. A database choice with trade-offs is using a graph database like Neo4j to store metadata relationships. The schema includes fields like file that has name, file direct path, data source, data format, created in yat, job ID, parent ID, data quality, score, and data retention policy. Indexing is crucial for efficient metadata retrieval. Pause and think. What's missing from the schema? Data lineage tracking is critical for understanding the data's journey and ensuring data quality. Audit fields are essential for tracking data changes and ensuring compliance. Having locked down metadata, we need to address scaling and performance. Caching is essential for improving query performance. We can use a distributed cache like Redis to cache frequently accessed metadata. Replication ensures data durability and availability. We use a 3x replication factor for object storage. Sharding allows us to distribute the data across multiple storage nodes. Bottleneck analysis involves identifying and addressing performance bottlenecks in the data ingestion and processing pipelines. Remember those 500 terabytes of data Netflix generates daily? To handle that volume, we need to implement horizontal scaling for our object storage and data processing frameworks. We use caching because it reduces latency for metadata lookups. Alternatives include using a traditional database, but a distributed cache offers better scalability. We can use consistent hashing to distribute the cache across multiple nodes. Here's the twist. Eviction policies are crucial to prevent the cache from overflowing. That said, there's a hidden problem here: reliability and operations. Fault tolerance is crucial for ensuring data availability. We use replication and redundancy to protect against data loss. Monitoring involves tracking key metrics like data ingestion rate, storage utilization, and query performance. Alerting involves setting up alerts for critical events like data ingestion failures or storage capacity breaches. Security considerations include data encryption, access control, and auditing. We need to implement robust security measures to protect sensitive data. Data governance is essential for ensuring data quality, compliance, and ethical use. The next piece of the puzzle is wrapping up and considering trade-offs. The main trade-off is between cost and performance. Cost optimization involves choosing the right storage tiers and data processing frameworks. Use cases for a data lake include customer analytics, fraud detection, and machine learning. Potential bottlenecks include data ingestion rate, query performance, and metadata management. Next steps include implementing data governance policies, setting up data quality monitoring, and building data processing pipelines. We gain flexibility and scalability, but sacrifice some of the structure and governance of a data warehouse.
Join our community of engineers mastering software engineering, algorithms, and technical skills. Subscribe to stay connected and never miss a tutorial.